Hello, this is Dr. Man. Today we're going to talk about special relativity mystery. You know, I've done some videos before about quantum physics and mysteries about quantum physics, how weird it was and why physicists were still using it. Crazy physicists, right? Yeah. So anyway, here I want to talk about special relativity. So there are many videos and tutorials and whatever on the internet right now, but I don't think they do a good job, at best. And sometimes they're wrong, actually, explaining why, there is a mystery behind special relativity. And I prefer to use the word mystery than other words like, people talk about the twin paradox and things like that. I don't like the word paradox because paradox means that there's something wrong, basically. While mystery, it may be weird, but you can solve it. And that's what we're going to do together. So much fun. Don't worry, we're going to have to use a little mathematics, but it's not really mathematics. It's just, arithmetic. Basically, we're going to use adds and subtracts and multiplies and divides, and that's it. No fancy stuff. So it's pretty easy to follow. What's more tricky is to interpret the results, and that's where a lot of the videos that I've seen so far on the internet and articles, fail, actually. So hopefully, this time it's going to work. Or not. Well, let's see that. Okay, so basically it will be kind of a crash course on special relativity. First thing first, we'll start with a short introduction and then we'll look at Galilean relativity. Yeah, there was relativity before Einstein. It was created by a guy called Galileo, an Italian guy. Crazy guy. But there were some problems with that type of relativity, so here comes Einstein that solves everything, well, almost, with the special relativity. And so he will explain, why we have relativity of space and time, and also some other guys, came up with examples to really explain the concept, which actually didn't work very well, but what's called the twins paradox. And actually it's not one, but several paradoxes. And then we can use triplets, instead of twins, 2, 3, 4, 5, 6, that's crazy. And then, of course, from that we'll draw some conclusion to see, how this affects our view of the universe. Wow, fascinating, right? Yeah. And then as a bonus, we'll get from special relativity theory, the derivation of the equation, E equal mc squared. Wow. Yeah, we can do that. It's not very complicated, actually. Again, all of this is not complex math. It's just that the interpretation is a bit tricky. And that's where, a lot of the videos I've seen so far have failed. But anyway, after that, we'll just, introduce a future series of videos that are maybe make on general relativity, which is more general, general relativity, more general than the special relativity. What's interesting is that relativity actually makes sense. It's not just a crazy theory for fun. It is a lot of fun, but still, what it says is that you can, take any measurement from anywhere at any time in the universe, and the same rules will apply. The same physical rules, the same mathematical rules. And that's very key, actually, especially when you start to talk about, particles or waves that go pretty fast. And it does have some non-obvious implications on space, the way you measure things, distances, but also time. And it is also subject to misinterpretations. In other words, you think you understand, pretty well what space is and what time is, but actually most of the time we don't. And Einstein has shown us a new way to understand those, obvious concepts, and showed us that we were wrong. And the problem is that although a lot of people know how to apply the rules that were defined by Einstein, sometimes they don't understand how to interpret them. And this is the purpose of this series of videos here, to make you really understand what relativity is about. And I hope it will work. Yeah, I hope so. Anyway, Galilean relativity. Yeah, as I said before, relativity existed before Einstein. And what it said, again, it was that the same physical rules apply for all Galilean frames of reference. There was no privileged frame of reference. But the question is, what is a Galilean frame of reference, right? But what is it? Well, it's pretty simple. It's like, you have a train like this, a car coming to me at a steady, linear, constant speed. And since there's no acceleration, by definition, I will call that a Galilean frame of reference. And it has some implication. The fact that there's no acceleration like this means, like, for instance, a guy inside the car doesn't feel any acceleration, or braking, like that. And when this guy is actually moving inside the car, well, you can use the car as a frame of reference, and say this guy was actually walking at 10 kilometers per hour. Now, if I'm outside of the car and the car is moving towards me with this guy inside the car moving himself, I have to be able to calculate the speed of the guy. I have to take into consideration both his speed, for instance, 10 kilometers per hour, plus the speed of the car here, for instance, 100 kilometers per hour. And then, to me, as a frame of reference from my perspective, this guy will be, moving at 110, 100 plus 10, So that was pretty simple, just addition. Okay, so if we want to formalize that, so again, we say the same physical rules, apply for all Galilean frames of reference. That means no acceleration. And you can apply that in particular, what we call space-time events, which means something happening somewhere, X, Y, Z, X, Y, and Z, and time, okay? And when you want to change perspective, for instance, you want to do measurements inside the car or you want to make measurements outside of the car, you have ways, mathematical transformations that you can very easily apply and use, and that will give you the movement as viewed from the guy inside the car or as viewed from the person outside of the car, for instance. And it's pretty easy, for instance, here, we'll have a frame of reference in black here, which will be for instance, me, and then this greenish blue frame of reference here would be the car, moving like this here. And assuming we pick the right origins for time and space. Then the transformation will be pretty easy. For instance, if we say there is, this point here moving on the x-axis, and at some time, I call it viewed from this frame of reference in black here, I call it F. If I pick a point on the x-axis here, I call it X. Well, the same point and at the same time, I can know its coordinate relative to the other frame of reference, the blue-green one, and that I will call x prime, and its value will simply be equal to x minus vt, v being the relative speed between the two frames of reference. So, pretty easy so far. And since here we're just talking about, linear movement here along the x-axis, it's pretty simple, and that means that the y and the z are the same, so therefore, there's no difference here. And since we suppose that time is absolute and is the same for everyone, well then t prime is equal to t. Well, at least that's what that is what the guys before Einstein thought was correct. Problems started to arise when instead of measuring the speed of a guy walking like this, we wanted to measure the speed of a light beam. For instance, this guy here, instead of just walking, would just have a lamp, and would send a light beam like this, and he wants to measure the speed of this light beam, by, for instance, measuring the time the light beam will take to go from there to the end of the car here. And well, if he has a good stopwatch, this is what he will find, roughly 300,000 kilometers per second. Okay. But now, if I want to measure, outside of the car, when the car is moving at the same time here, if I want to measure the speed of this light beam here, well, I have to take into consideration the speed of the car, and as we've seen before, the speed of the light beam here. And what we did before was just adding the two. But the problem is, if I do that, well, actually what I find will be exactly the same value here. In other words, just like if the car was not moving. That was a pretty bad news, because what that meant was that Galilean relativity and constant speed of light were incompatible rules. Oh my God. And so what happened? Well, either the Galilean relativity rule was wrong or the constant speed of light rule was wrong, or both. But, it had been measured very, very precisely, hundreds of thousands, millions of times, and people were sure that the speed of light was actually a constant that didn't change from wherever you were measuring it. So, was it the Galilean relativity rule? This very simple rule and very natural rule. If something moves, you just add the speed of what's inside to what's outside, and then you get the total speed. What can be wrong with that, right? Well, there was something wrong there, and that was a big trouble, big problem, and it started to becoming more and more important because we were starting to measuring things that were going faster and faster, and getting close to the speed of light. So, what you do? Well, you call Mr. Albert Einstein, and he comes and solves everything. Well, almost everything. And that's what we're going to see in the next videos. Wow, how exciting.